November 1995, American Airlines Flight 1572, an MD-83 jet, is making what should be a routine approach into a stormy Connecticut airport. But miles before reaching the runway, the aircraft is rocked by a sudden impact. Despite being 771 feet in the air, the aircraft is violently scraping against the tops of pine trees. 15 years later, Cathay Pacific Flight 780 is cruising over the South China Sea. As the pilots prepare for their descent, both engines on the Airbus A330 stop responding to throttle commands. The crew manages to force one engine back to life, but the emergency is far from over. As they line up for a high-stakes landing, that engine locks itself at 74% power, pushing the plane toward the runway at a dangerous speed. Both crews brought their passengers home safely, but unless investigators can explain exactly why these systems failed, these unsolved mechanical mysteries remain active threats to every other aircraft in the sky. To understand why Flight 1572 descended into the tree line, investigators turn to the forensic data stored in the flight recorders. The data shows the aircraft was dropping at 1,000 feet per minute, double the normal descent rate. In the rush to reach the runway, the crew missed their minimum descent altitude, the critical verbal check meant to keep the plane clear of ground obstacles. The investigation found the invisible culprit in the control tower. Distracted controllers provided an outdated atmospheric pressure reading to calibrate the altimeter. By using that incorrect 29.15 setting, pilots saw an altitude 76 feet higher than their actual position. A single officer momentarily looking out the window, combined with that missing decimal point of data, turned a standard approach into an invisible trap. In the Cathay Pacific investigation, the evidence pointed to a total mechanical disconnect. This graph shows the pilots pushing the throttle forward, while the fuel flow into the engines remains completely flat. The onboard computers logged an error specifically at the main metering valve, the hardware responsible for physically regulating the amount of fuel entering the engine. Investigators took the valve to a UK lab and sliced it open. Inside the precision-engineered component, they found a bizarre white powder jamming the mechanics. The forensic analysis revealed that this unknown contaminant had entered the fuel system and slowly suffocated the engine's power supply from the inside out. To find the source of the contaminant, investigators put the powder under an electron microscope. Analysis revealed the powder was a super-absorbent polymer, or SAP, which is used to soak up moisture. Critically, these particles were coated in salt crystals. That salt trace led investigators to an underground fuel pipe in Surabaya, Indonesia. During recent construction, ground salt water had leaked into the airport's fueling system. High-pressure salt water hit the fueling truck's internal filters, destroying the protective mesh and releasing millions of SAP spheres into the plane's fuel tanks. Inside the aircraft, these spheres absorbed moisture, swelling into a thick gel that clumped and blocked the engine valves. A tiny, invisible leak in a pipe thousands of miles away had cascaded directly into a life-or-death crisis over the ocean. Back in the cockpit of Flight 780, the pilots had no way of knowing their fuel system was contaminated. With one engine jammed at high thrust, they were forced to attempt a landing at 100 knots over the safe limit. The touchdown was violent. The crew applied maximum braking, causing the tires to disintegrate and the wheel temperatures to hit 1,000 degrees as passengers scrambled down the emergency slides. For their skill in manually overriding a failing automated system, the pilots were awarded the Polaris Award, the highest honor in civil aviation. These incidents highlight a core paradox of aviation. We build these aircraft as massive engineering marvels, yet they remain vulnerable to a single decimal point in a weather report, or microscopic spheres of plastic. We rely on human pilots to navigate these failures in real time, but long-term safety depends on the investigators who dissect these near misses, ensuring a single data error or a hidden contaminant never causes a catastrophe again.